about rational numbers. In this lesson, you should be able to answer the question, how can you represent rational numbers on a number line, as decimals, and in real-world situations? Let's look at some of our lesson goals. In this lesson, you'll be able to use rational numbers in real-world situations. You'll also plot and compare rational numbers on a number line. Finally, you'll be able to write rational numbers as fractions and as terminating or repeating decimals. There are 4 words that you need to know throughout this lesson. The first word in green is a general academic word, equivalent. The next 3 words are domain specific, rational number, repeating decimal, and terminating decimal. In this lesson, we're answering the question, how can you represent rational numbers on a number line, as decimals, and in real-world situations? Have you ever used a measuring tape? A measuring tape is a real-world example of a number line. The marks between the integers on the measuring tape represent units of measure, such as 4 1/4 inches. In this lesson, we'll be looking at the numbers in between integers on a number line. Let's start by reviewing how to represent integers on a number line.
All right, I want you to take a second and I want you to draw -3 on the number line, then answer the following question. So first, let's work together and let's draw -3 on the number line. So here we go. On the number line, we'll put 0 right here, okay? And then negative numbers are on the left side of the number line. So I know -3 is going to go this way, and let's just count 1, 2, 3. So I know this is -1. This is -2, and here's -3. All right, how many of you got that right? And that's where you put -3. Awesome. All right, let's go to the next question, which is asking you this. I want to give you a second. I want you to use the number line that we just created, and you are going to plot -3, 1, and 3, and then you're going to select which statements are true. All right. Okay, let's do it together. All right, my number line is kind of messy. Okay, so we're going to plot -3. Now we know we had 0 in the middle. We had -3 over here. Then we know 1 is right before 0 because it's on the positive side. And 3 would be right here, okay, after 1. And all right, so now we're going to discuss what is true. All right, so is -3 greater than 1? And if we look back on our number line that we had plotted, we have -3 here. We got 0 in the middle. We got 1 here. And then we got 3 here. We notice -3 is to the left of 1. So -3 would not be greater than 1. Okay. Is negative 3 equal to 3? Well, we can see negative 3 and 3 are not at the same spot, so they are not equal, right? Is 1 less than 3? Well, 1 is to the left of 3 on the number line, right? So that means that 1 is less than 3. Okay. Is negative 3 less than 1? Again, look, negative 3 is to the left of 1. So that would mean negative 3 is less than 1. All right.
In this lesson, we're answering the question, how can you represent rational numbers on a number line, as decimals, and in real-world situations? In the warm-up, you looked at integers on a number line. Integers are part of a larger set of numbers called rational numbers. Let's take a look at this type of number. A rational number is a number that can be written as a fraction in the form a over b, where both a and b are integers and b cannot equal 0. Rational numbers can be positive, negative, or 0. Let's look at some examples. The integer 4 can be written in the form a over b by writing it as 4 over 1, or as 12 over 3. Negative 10 could be written as negative 10 over 1, or even as negative 20 over 2. The rational number 0 could be written as 0 over anything, such as 10. Next, let's look at some mixed numbers. Mixed numbers are rational numbers that can be written in the form a over b by turning them into improper fractions. To do that, we take the denominator of 4 and we multiply it by the whole number of 2 to get 8. Next, we add the numerator of 3 to get 11. We keep the denominator the same, 4. This gets us 11 fourths, which is equivalent to 2 3/4. Let's try it again with 10 1/2. 10 1/2 is another example of a mixed number. To turn it to an improper fraction, we follow the same steps. 2 times 10 is 20, plus 1 is 21, over the denominator of 2. 21 over 2 is equivalent to 10 1/2. Next, let's look at some other numbers that can be represented as fractions. Terminating decimals and repeating decimals are examples of rational numbers. Terminating decimals are decimals that end or terminate. The number 3/10 is written just like it sounds, 3 over 10. Negative 16/100 is also written exactly as it sounds, negative 16 over 100. Of course, we can turn this into a simplified fraction by dividing the numerator and the denominator by 4. This gives us the equivalent fraction of negative 4 over 25. Next, let's look at 3 17/100. 3 is still our whole number, where 17/100 is our fractional part. Of course, we need to write our rational numbers in the form a over b. To do that, we take our mixed number and turn it back into an improper fraction. 100 times 3 is 300, plus the 17 is 317 over 100. Looking at repeating decimals are decimals that repeat in some sort of pattern. They go on and on forever. 3/10 repeating is an example of a repeating decimal. This can be written as a fraction as 1 over 3. 0.16 repeating can be written as the fraction 1/6. And negative 1.2 repeating can be written as the fraction negative 11/9. If a decimal does not terminate or repeat, it is not a rational number.
All right, guys, if we look at the number options that they give us and we identify what is rational and what is not rational, notice 0.63 is identified as rational because we can write this as two integers, a fraction of two integers. This could be 63 over 100. All right. Negative 15.5 is rational because it can be a fraction of two integers. Remember, this is just a mixed number. This is just negative 15 and 5/10, right? Uh-oh, and it's zooming in. Okay, so this is negative 15 and 5/10. And I can make that into a fraction of two numbers by just simply multiplying 15 times 10, the denominator, which would give me negative 150. And then I would add 5 to that. And that would give me negative 155 over 10. Right? So I know that that's rational. Negative 11/4 is already a fraction of two integers, so I know it's rational. And 2 and 1/2 is a mixed number. Again, we can turn it into a fraction of two integers by simply multiplying the whole number times the denominator. 2 times 2 is 4. Then adding the numerator plus 1 is 5. So we know 2 and 1/2 is just 5 over 2, right? All right. So let's go ahead and look at the not rational options. If we look at the numbers that are not rational, notice the numbers that are not rational do not repeat in any fashion. Okay, so we have these decimals that just go on and on forever, and they don't have a repeating decimal. Okay, it's just the first one, 3, 1, 4, 5, 8, 7. It's just going on and there's no pattern. Okay. Same with the next one. That is the difference between rational and irrational numbers.
Imagine a swimming pool. The surface of the water is the midpoint between the bottom of the pool and the diving board. So we'll represent the surface of the water with the number 0. All of the numbers above 0 are the positive integers. The numbers below 0 are the negative integers. The diving board is 3 meters above the water. We'll represent that here. Diving safety recommends that the pool be 3 7/10 meters deep. If the surface of the water is 0, where on the number line would we represent the depth of the water? 3 7/10 is between 3 and 4. But we're looking at below the surface of the water. So we are looking at between negative 3 and negative 4, but a little bit closer to negative 4. We can represent the depth of the water here. When a diver jumps off the diving board, she jumps up 3/4 of a meter. Her feet are now 3 3/4 of a meter above the surface of the water. We can represent that between 3 and 4, but a little bit closer to 4. The diver performs her dive, and when her hands hit the water, her feet are about 1 8/10 of a meter above the surface. 1 8/10 is between 1 and 2, but a little bit closer to 2. This is where her feet are now. Overall, she dives about 2 1/4 of a meter deep. This is the rational number negative 2 1/4 because we're now below the surface of the water, or as the improper fraction, negative 9/4. Negative 2 1/4 is represented between negative 2 and negative 3, but a little bit closer to negative 2. This is where her dive ends up. at graphing rational numbers on a number line. Graphing numbers on a horizontal number line is the same as graphing them on a vertical number line. Everything to the left of 0 is a negative integer. Everything to the right of 0 is a positive integer. Let's try some examples. First, let's graph negative 4 and 1/3. Negative 4 and 1/3 is between negative 4 and negative 5, but closer to negative 4. It isn't quite a half, though. This is where we can plot negative 4 and 1/3. Next, let's try negative 2 and 3/4. Negative 2 and 3/4 is between negative 2 and negative 3 on the number line, but closer to negative 3. It's actually halfway between negative 2 and a half and negative 3. Here is negative 2 and 3/4 on a number line. Next, let's try some positive integers. 1½ is a positive number that can be expressed on a number line. 1½ is between 1 and 2, halfway between. 3 and 1/10 is between 3 and 4, but much closer to 3 than 4. 3 and 1/10 is located here on a number line. Finally, let's plot 4 and 1/3. 4 and 1/3 is between 4 and 5 on the number line, but closer to 4. 4 and 1/3 is the additive inverse of negative 4 and 1/3. It's called an additive inverse because it's the same distance from 0 on the number line. Negative 4 and 1/3 is the same distance from 0 as positive 4 and 1/3. Every rational number has an additive inverse on the number line. All of these fractional numbers on the number line also have a decimal equivalent. For example, negative 4 and 1/3 is equivalent to negative 4.3 repeating. Negative 2 and 3/4 is equivalent to negative 2 and 75 hundredths. 1½ is equivalent to 1 and 5/10. 3 and 1/10 is equivalent to 3.1, 3 and 1/10. And finally, 4 and 1/3 is equivalent to 4.3 repeating. You've been answering the question, how can you represent rational numbers on a number line as decimals and in real-world situations? You can now graph a rational number on a number line. Next, you'll learn how to convert a rational number from a fraction to a decimal. You've seen that terminating and repeating decimals are rational numbers. Let's write the decimal equivalent for 7/25. The denominator 25 is a factor of 100. To write a decimal equivalent, we first need to find an equivalent fraction with a power of 10 as the denominator. 25 times 4 is 100. When we do the same to the numerator, 7 times 4 is 28. 28 over 100 is written as 28 hundredths, 0.28. This is a rational number because it ends. It terminates here at this place value. Let's try another example. 63 over 500 is equivalent to another fraction with 1,000 as the denominator. 1,000 is another power of 10. 500 times 2 gets us to 1,000. 63 times 2 is 126. 126 thousandths is written as 0.126. 126 thousandths, also a terminating decimal.
All right, so it says, can you find a fraction that's equivalent to 6 over 25? which of the following terminated decimals is equivalent to this fraction? Well, first things first, we want to have the denominator either be over 100 or over 1,000, okay, or over 10. Now it's easier for us to take 25 and move it to 100. The reason why we want it over 100 is because it's easier for us to convert it into a decimal without a calculator. So what I'm going to do is I'm going to look at the denominator 25 and think of it as money, right? It takes 4 quarters to equal $1. So I'm going to multiply the denominator by 4. 25 times 4 is 100, right? 4 quarters equal $1. So that means that I can change now the denominator to 100. I have to do the same thing to the numerator, multiply it by 4. So that means that 6 times 4 is 24, all right? So I end up with the fraction 24 over 100. So that means if I have to change this to a decimal, I can change it to 0.24 or 24 hundredths, which would be there. If you're using your calculator, simply take the 6 over 25 and your calculator, this bar here on the fraction is a symbol of division. So if you want to change it into a decimal, you would convert this into a decimal by typing 6 divided by 25 in your calculator, and you should get the exact same answer, 0.24.
A rain gauge shows 7/8 of an inch of rainfall. Let's write this fraction as a decimal. 7/8 has 8 in the denominator. You can't multiply 8 by a number easily to get a power of 10. Instead, we'll need to use long division. 7/8 can be written as 7 divided by 8. 8 does not go into 7, so we add a decimal and a 0. 8 goes into 70 8 times. We also move our decimal point up into our answer area. 8 times 8 is 64, and when we subtract, we're left with 6 left over. Let's bring down another 0. 8 goes into 60 7 times. 8 times 7 is 56. 60 minus 56 leaves us with 4. Let's bring down one more 0. 8 goes into 40 5 times. 8 times 5 is 40, leaving us with no remainder. Therefore, 7/8 is equivalent to 875 thousandths. Let's try some more examples. Let's start by writing the fraction 4/9 as a decimal. 4/9 is written as 4 divided by 9. 9 can't go into 4, so we add our decimal and 0. Let's move our decimal point up, and 9 goes into 40 4 times. 9 times 4 is 36, leaving us with 4 left over. Let's bring down another 0. 9 goes into 40 4 times again. 9 times 4 is 36, again leaving us with 4 left over. I hope you're starting to see a pattern here. You should see that 4/9 is actually a repeating decimal. 4/9 is equivalent to 0.4 repeating. Let's try 1 and 7/30 now. 1 and 7/30 is a mixed number. Let's make it into an improper fraction to get us started. 1 and 7/30 can be written as 37 over 30. Again, let's use long division to find our decimal number. 37 divided by 30. 30 can go into 37 once. 30 times 1 is 30, leaving us with 7 left over. I don't have anything else to bring down, so here's where I add my decimal and 0. Let's bring that decimal up so we don't forget about it. Bring your 0 down and 70 2 times. 30 times 2 is 60, leaving us 10 left over. Let's bring down another 0. 30 goes into 100 3 times. 30 times 3 is 90, leaving us with 10 left over. Let's try another 0. 30 goes into 100, again 3 times. You should notice that this 3 is repeating. 1 and 7/30, or 37 over 30, is also equivalent to the decimal 1.23 repeating. Notice that the 3 is the only number here that's repeating.
All right, now we're going to do a sample problem. We're going to change 5/16. It says a drip bill has a size of 5/16 inch. What is this measure as a decimal? So let's change this to a decimal. Now, we are not going to use our calculators. I know you guys can use the calculator now. You know, and we'll talk about what we'll do if we put this in the calculator, but let's try this using long division like they did. Okay, so first we need to take our numerator, so 5, and what I say is our numerator goes in the house, okay? So 5 is in the house. Our denominator goes outside the house. So 16 is outside the house. Now, 16, 5 divided by 16, right? 5 can't be divided by 16. So we're going to add a decimal point, and we're going to add a 0. And in our minds, we're going to think 50, okay? So how many times can 16 go into 50? And I just think of the number. If I double 16, I'll get 32. That's a little bit too small. I think we can go higher, right? If we think of 16 times 3, okay, that would give us 48. All right, and so I know that the highest we can go without going over 50 is 16 times 3, because if we go 16 times 4, that we would be way over 50. So we don't want to go over 50. So we can go, 16 can go into 53 times, and if I multiply that, 3 times 6 is 18, right? 8 carry my 1 up here, and then I think 3 times 1 is 3, plus a 1, and I'll just show you, carry your 1, plus that 1 is 4. So I know 3 times, there we go, 3 times 16 is 48, okay? Now, let's subtract, okay? If we think 50 minus 48, we would be left with a remainder of 2, okay? Now, I'm going to add another 0, and I'll bring that down, bring my 0 down, and I think 20. And then I just ask myself, hey, how many times can 16 go into 20? And if I think about that, 16 can only go into 20 one time, right? And so if I multiply 1 times 16, that's just 16. All right. And then I subtract. And 20 minus 16 is 4. Right? And I can add another 0 if I want and bring it down, and I can keep going. All right. But what we got right now, we got 2 decimal places, and I'm going to move my decimal up. And I know that 5 divided by 16 is 0.31. Okay, it's 0.31. Now, here's the thing. If I want to put this in my calculator and I want to see what this is as a decimal, I would just punch in 5 divided by 16. Okay, so either way, We can do it the no calculator way, do long division, or we can do it the calculator way and we can find out the decimal doing division.
We can also use a calculator to rewrite our fractions as decimals. For example, if we have the fraction negative 9/20, we can rewrite that as negative 9 divided by 20. Now let's put that into our calculator. We'll input the 9, then the negative sign, divided by 20, equals negative 4500. Let's write that as our answer. Equals negative 4500. Now let's try 5/6. 5 divided by 6. Let's put this into our calculator. We'll clear this out. 5 divided by 6 equals, we have a decimal point, an 8, and then a 3 that seems to be repeating, but with a 4 at the end. That means that the calculator is rounding our decimal. The actual answer here is 0.83 with the 3 repeating. So we'll rewrite that using our bar notation. Our answer is 0.83 with a bar notation over the 3. Let's try this with another fraction like this. If I have 7/6, 7 divided by 6, let's put this into our calculator. We'll clear out our last problem. 7 divided by 6. You notice this is an improper fraction, so we have a whole number, 1.16, repeating. Again, our calculator rounds this fraction at the end up to 7, but we know that we can rewrite this using our bar notation. We'll rewrite our answer as 1.16 with the bar over the 6, since the 6 is what's repeating. Now, if I have 12/17, again, we can rewrite this as 12 divided by 17. Now watch what happens when we put this into our calculator. We'll clear this out. 12 divided by 17. Now here we get a decimal that doesn't seem to end or repeat. However, because it's a fraction, we know it's a rational number. So therefore we know that eventually it must end or repeat.